draft science video. So I think I'll do one more electricity. I have to write it up and I'll add it to the paper before I submit to a new place. And we'll see how it goes. But yeah, it's just too good. Anyway, holiday. I don't follow. When your drawing turns into scribbles over scribbles, it becomes unclear. Blah, blah, blah. You know, not a very useful comment. I mean, you could have given me at least a time code where, oh, it all goes funky for me at this time code or something. But anyway, for the sake of whatever, I'll go through it real quick. Alright, so the idea is there's a field, okay, of quanta, like photons, except they don't have a frequency necessarily. They're not associated with each other by frequency or necessarily by polarization. And yeah, and matter is those things caught in swirls, and they have a polarization, an orientation to the world. It could just be the plane that they exist on, like a galaxy, but no need to get into that. The point is that in the process of magnetism, and at least in electricity, there's a phenomenon where the electrons, the negative little bits, when this field energy goes in, it comes out polarized in such a way that other electrons absorb that quanta. So where most of the stuff might go through you, and only a certain percentage, a low percentage, you might interact with, if it's of this particular polarization, you're more certain to interact. So you could say that the field energy is random, and that there's, say, 1% of it is of this polarization that electrons absorb, which means they acquire, they eat it like a Pac-Man, and it gives them energy, so to speak. They absorb the energy of the graviton in the sense that it has a velocity, and so you just spread that velocity over all of the photons, all of the quanta in the thing, and by that math you will figure out how much extra velocity the thing will acquire. So it'd be a very small velocity per photon. For, say, something the size of a human, it would be a infinitesimally small velocity. But for individual atoms, it could be, you know, a quanta of distance. Anyway, so the basic mechanism is that that polarization makes electrons repulsive to each other, in the sense that if if I expel one to a partner that's polarized, he will absorb it, and that one will be going, because I expelled it into his direction, he'll acquire that direction, which will mean he'll tend to drift away from me. Now the other half to that story is that there are certain polarizations created by this positive polarizations that would be, say, created by protons. So when stuff goes into them, it comes out in this positive form. And it has the same effect, wherein that polarization is zero to an electron. So electrons, if you expel at me zero polarizations that don't have an effect, then the field pressure behind me will push me towards you. So I won't be attracted to you. I'll be effectively pushed to you, because you're breaking what would have affected me. And it could reduce to just the one electron polarization. In the sense, you could probably make the whole thing work by just using the electron 2x zero effect, where the 2x effect, let's just leave it at that. But I don't want to confuse anyone, you don't want you to get lost, but just understand that through polarization and through having a magnified effect of being more absorbable, that you're more likely to absorb energy in that polarization, you could kind of figure this whole thing out in terms of what happens to everything based on that function. it explains the magnetic and the electrical forces, certainly. Alright, so now let's just do the quick thing on the conductor. The conductors are, it's just the layers of plus minus in most matter. The atoms arrange themselves in such a way as that they are predominantly one thing on one side, more proton is exposed, and on the other side it tends to have more electrons exposed, that kind of thing. So there's a tendency to layer, and on the surface is where these electrons do most of this work, in the sense of they get acquired or they get stripped. If they're stripped, then the protons are more dominant and there's less negative polarization, and if or put more simply, there's less negative polarization, and if there's an abundance of electrons, then there's obviously a higher density of this polarizing film, and you're more likely to create polarization that other electrons will find repulsive, in the sense that they'll absorb the energy of that field and move in the direction of that field. That should be simple enough. Alright, so the simple way for me to try to illustrate this, I won't bother spinning coils and all that kind of stuff. We'll just take two conductors. So I put a voltage into one of them, let's say minus 150 volts, just to keep it electron strong. And the other side is connected to the ground. And so what you can think of it as this voltage goes across, it gets weaker. So what's really happening is there's a flood of electrons at one end, and then it gets thinner and thinner, and finally goes to zero, and when it's balanced, in the sense. So the balance isn't no electrons, it just means that there's the minimum, a number that is what things will tend to when you add them all together, when you throw them all together, what will be on the normal level. So there'll be like a normalized level that we would call ground or neutral. It's neither too hot or too cold, so it's somewhere in the middle. For the purpose of this drawing, I just made it 0 just to make it simpler, but you could think of it as being halfway up. So anyway, this is the field intensity, the strength. Now when they often draw field lines, they kind of have they draw them in this opposite way, where there's a lot tightly bunched field lines, it's where the force is strong. And in a sense, that's sort of deceptive, because what you want to do is recognize the depth or the reach of the field is more important than anything else. It's how far out the field goes with what intensity. So anyway, so what happens is if I keep pumping, because I have a constant power supply here, so we'll just draw that little plates here. So here's our negative and our plus voltage, and the plus being tied to the neutral. I just keep pumping 150 volts into here. So this is what you're getting. Now if there was another wire or coil of wire on this other side, what this is essentially doing to it is creating this opposite effect in it, in the sense that now this is a thick polarization level, so there's a lot of this double polarized, the electrons will absorb the field energy, so to speak. They will accelerate, they will in a sense be repulsed, but it's not technically repulsion. Well, I guess it technically is in this sense. It's never attraction, it's always some form of repulsion. Well, anyway, so they will be pushed by this strength of this field in to end up putting a voltage now over on this other wire at the other end. So essentially you can see those two parallel lines, and that basically that's what first forms, is that the extra pressure here pushes this thin, because it's more pressure. So you just have to think of this as extra pressure, stronger pressure, and it bulges here at this other end because there's no pressure. So now we have the negative 150 volts at this end of this conductor. Let's put it back to a battery. And now there are two interesting things happen. The first interesting thing is you can kind of see it as this voltage now will be doing the same thing to this conductor, in the sense that it's creating a pressure that's going to try to prevent electrons from moving this way. So these electrons are going to tend to move this way, and these are moving the opposite way. This is going to tend to not allow these electrons to do what they want to do, which is go that way. And so it's like this is a it sort of stifles momentum, and everything in a sense will end up getting neutralized or neutraled out. Now the other thing you can look at it as is that once this is established, so I don't know if this is the part where Hothovec didn't follow along, but if you keep pumping 150 volts in here, what happens is that this pathway back to well, this is just a closed circuit, let's see, or just a resistor in here. This pathway will not allow electrons to come through, you see, because you have a high pressure here. You're squeezing this pipe. You can think of it as just squeezing it almost closed, because it's high. There's a high runaway factor in that you'll be accelerated by this field. When the field hits, the electrons will absorb the field and accelerate away. And so they're accelerating in the wrong direction, in the sense that they're going to escape going through the conductor the right way. So in a sense you have just a block, and the voltage can't move because it can't refill this with electrons and then have them push through again. And so you have two effects. First, you have this wall here that's creating a wall against this movement, so the two are ending up fighting each other, and they end up with kind of a neutral. They both end up the same height, so to speak. And you have the effect where if they don't, because you keep pumping 150 volts at this end, you just have a dam here. Nothing can get through, because the electrons that want to get back into this conductor can't get back in, because this field is accelerating them in the opposite direction. So the voltage can't flow. And so that's why DC current won't work in a transformer, because there's no way to continue to push the voltage, because it basically establishes this dam. And so by alternating the current, alternating current would be essentially, first you create the wedge this way, and then you create the wedge in the opposite direction. And by doing that, you keep refilling this part of the field with electrons, so that when this part of the field goes high again, there'll be electrons there to push this way. So you'll keep filling it so you can push it, and fill it so you can push it, fill it so you can push it. So alternating current keeps refilling the conductor with electrons, so now they can be pushed. But if you don't allow the bucket to be refilled, which DC current cuts off the refilling process, the current won't flow. So, I don't know if there's a whole bunch to go through. Again, it's just it's the same as the magnetism thing, in the sense that once you get this idea that it's about absorbing velocities, which is acceleration. So it's about accelerating particles and accelerating them with a field, okay, that has a polarized bias in it. And depending on the polarized bias will decide whether you absorb the force behind you, or whether you absorb the force coming at you. Just depends on what polarized bias there is in that 1% of the field. And again, if in magnetism it's more than 1%, because most or a more substantial part of what's going through the filter is getting polarized. So its effect on the electrons is much more dramatic in terms of their acceleration and their ability to move things along. The way they're moving the proton, so if you just think of the electron, and here's the proton, the electron is, as stated, anything goes through comes out polarized, and it's polarized in a way that is invisible. Okay, so we use a dotted line to protons. So the proton doesn't see all of the gravity, so to speak. So the gravity field is coming from all the way around. The proton doesn't see the gravity that goes into the electron. It comes out polarized. And so it doesn't see that. It doesn't feel it. It doesn't react to it. It can't absorb it. But it is still absorbing pressure from the field external. So it ends up with more pressure from the field. It absorbs more arrows by over time. It ends up over a period of time. It'll end up absorbing more going this way than that way, and therefore it will accelerate towards the electron. So as you move electrons, in a sense, you'll move protons, because the electrons will create a field next to the proton that will allow the proton to absorb that field, the field behind it. But that's how everything moves. Nothing moves because it's banged into. It moves because it absorbs field. And if the field has been biased through polarization, biased in a direction, it will move in that direction. So that pretty much says it, I think. So yeah, if you don't understand, I don't know what to say. Yeah, sorry. But you have to ask more specific. You have to have it more specific. I don't get something more specifically because I don't know what it is you don't understand. Polarization is kind of that's an understandable concept to me. The idea that you're filtering. The filter is basically running on absorption. So you absorb. It's like a surface absorb. Like some surfaces absorb infrared light and then reflect ultraviolet light. That's a kind of polarization. It's a kind of, yes, I'll accept one thing, I won't accept the other thing. And so it's that kind of effect. The electrons will absorb energy in one form, they won't absorb it in another form. And through that mechanism, the pressure field dynamics will kind of decide the fate of them. They will move as they're obliged to absorb velocity in a direction based on field pressure. And this idea of this wedge, understanding that these parallel lines being established, and just the obvious imbalance that would create in terms of provoking a velocity, and then the idea that that wedge also has the effect of making it impossible to refill because it restricts the pressure. I don't know how else to say that. Yeah, that's good enough for now. But yeah, I mean, having added electricity, this is a rational explanation for the function of current moving through wires. And it works really well for all of the static charge stuff, because that's all, again, it's like you can almost see the film when you think about it as being polarized, and you think about the metal is now polarized and that it's creating a different kind of energy. When the stuff goes through it, it's irradiating a different kind of radiation when it has charge on it. And then it makes it perfectly understandable why why electrons move based on that polarization. So this wasn't as good as I was hoping for, but again, I mean, I have to write it, and writing's so irritating, and I don't even like thinking about it. But it's the strength of the field, not the movement of the electrons. It's really important. Again, just that 2 times increase in the likelihood of absorption just explains it all. That bias makes it possible to create substantial differences in fields that appear to be the same. I mean, we can't see any of it, so you know what I mean. I mean, if we could see all the different kinds of radiation flying around us, then this would be so much more intuitive. Because it would just be obvious that, oh yeah, look, radio is very different than this, and it's very different than that. We'd see all the differences in the volume and the character of these different photons moving at a frequency. I suppose if people could understand light as these little bits, I mean, I think this whole, see, I just never, it's very rational for me to think of particle light, just because I never, you know, even though I saw, like, I remember my you know, grade school textbooks having the wave thing above the electromagnetic spectrum, and I just never saw the wave. I just never saw it that way. I saw it as a, it just seems so obvious that, I mean, it's a thing separated by a distance. You know, that's a frequency. You know, that's the wavelength. What's the other word they use? Period. I mean, you got, there's some other one, right? But, you know, they got 4 terms to describe one event, which is just the distance between 2 of these things. And that just always seemed so obvious. They're just little things moving the speed of light, and if you have a row of them having the same distance between them, you'll be able to detect them as some form of radiation. So anyway, I'm just saying that that's why maybe this all makes more sense to me, thinking about fields of little bits moving the speed of light, because it's kind of what I always thought was happening anyway, pretty much. And I never saw any reason to not think so. I just, you know, there was no real hard evidence that there was any reason to add any other feature to light. The frequency was pretty much everything. The difference between ultraviolet and infrared was the frequency. There's nothing else that's different. Obviously, you can fit more ultraviolet light in the same amount of space. Cat's fighting. But that's it. I mean, it has more energy in that sense. It's more energetic, more powerful in that sense, because there's more of it, you know, per square inch. Anyway, that's a side subject. But it really isn't, because electricity is pretty much just light. It's all light. Well, electricity is a little different just because it is, the electrons are giving you a visualization of the field. The electrons are being moved by the field, so obviously the field has to be, in a sense, moving the way that the electrons are moving. The electrons aren't floating in it, they're being accelerated in it. But the only way they could be accelerated in it is that the field has to have a strong bias in the direction of the electrons. So if you follow the electrons, you'll be able to trace the field, because the electrons are doing what the field basically is saying. More field, more electron pressure on one side, the electrons will move to the other side. They'll always try to evade each other. They'll always end up evading each other, because being in each other's presence will mean I will be spewing energy you will consume. It's like I was a light bulb and you were a light bulb, and the light you were emitting made me move, and the light I emitted made you move. It's exactly the opposite of gravity. Well, they're both the same thing, but I mean it's exactly the opposite in the fact that what you do is what I make you do, and what I do is what you make me do. Just like the Earth does what the sun tells it to, and the sun does what the Earth tells it to. The two arrangements aren't woven together. They're separate arrangements, separate events. Yeah, that's a good way to put it, maybe. The fact that I emit light has nothing to do with me. I'm not affected by it. The sun isn't affected by the gravity it has. You're affected by it. Well, obviously this stuff in the sun is being pulled to the center of the sun, so technically the sun is, but you know, I'm trying to use this in a bigger picture kind of way. Just as if I was a light bulb, I'd have to produce the light, and producing the light means you'd have to reduce me to the center point where the light comes from. But anyway, Oakley doke, enough. So, I will try to resist making anything else but a more perfect video next time, but I think this is enough for you to get it. I mean, I just don't know if I need to go explaining everything about currents and charge. I think people who know something about the subject will understand that this is the most important concept in electricity, is this induction. And once you understand this force mechanic, it applies to everything quite easily. Quite understandable. Oakley doke. So, I need somebody that's capable of making videos or making arguments or something. I got to find a better. I got to find some kind of more reasonable feedback, because I just don't get any. This idiot here, one human here, can't. He's talking about this stupid camera guy, that Tesla nut. Who thinks he can bend light with his magnets. Ken is legit, and so is Tesla. Ugh. Right, says you. Legit in what sense? You provide no mechanism. You might as well just call it bent space, calling it perturbation, call it ether, without giving it any character, any pieces, or any object. If you can't draw a picture of it, it's not very useful. I mean, really, you should be able to model this with something. There should be some kind of Play-Doh or silly putty that you can make a model out of to make it somehow understandable how what your wavy bullshit is doing. If you want to debate him and disapprove his work, then I suggest brushing up on your opposed view. No, what the biggest problem is apparently is he can't figure out how to hit a button on the open room he has that says, yeah, let other people in the room. He can't figure out how to grab the link and send it, email it to somebody. So I guess it's really not my problem. It seems to be his problem, which is, I think, he's a fucking coward, okay? So what else can I say? I pretty much begged him to allow me to, actually speak in the room, not type questions, which seems quite ludicrous. But whatever. As you should know, since you can't even finish sentences with periods and shit, retard. 'Cause it doesn't appear you have one to debate with. So that's a counter argument. You've read my paper, you've done something reasonable in this, or you're just making, of course not. Oh. I mean, it just amazes me that this asshole, I don't know, would you think I'm going to be impressed by this comment? That's going to somehow change my mind? Or it's just going to make me say, holy shit, humans are so fucking dumb. I mean, there's really no excuse for us to eat pigs. We should be eating these assholes. These people are so fucking dumb. I'm trying to think of something. We should just make flooring out of them. Like roll flooring. That's what we should do. Window treatments. Lampshades. You are way too dumb, motherfucker. That's what I'm saying. Yeah. You're way too fucking dumb. You're an offense. You are you just shouldn't be allowed to waste the calories you're consuming to run a brain as useless as yours. Idiot. Anyway, till next time.